Imagine swinging a stone tied to a string around your hand. Even if you spin it at a constant speed, its direction keeps changing. This is what we call circular motion, the movement of an object along a circular path. When the speed remains constant throughout the motion, we refer to it as uniform circular motion. While the speed is unchanged, the direction of motion changes continuously, and that change in direction results in a kind of acceleration. This is why uniform circular motion, though steady in speed, is still a type of accelerated motion. Examples of such motion include satellites orbiting Earth or a fan blade rotating at constant speed. Let's talk about linear velocity. In circular motion, linear velocity is the speed at which the object moves along the circumference of the circle. But unlike straight-line motion, here the direction of this velocity is constantly changing. It is always tangential, that is, at a right angle to the radius at any given point. For uniform circular motion, this tangential speed stays the same, although its direction shifts every moment. The linear speed is calculated using the formula v equals to times pi times radius divided by the time period. That is, how much distance the object covers in one full rotation divided by the time taken. Now, in addition to linear velocity, there's another way to describe circular motion, angular velocity. This tells us how fast the object is rotating or sweeping edges. It is denoted by the symbol omega and is calculated as angle in radians divided by time. For example, if an object completes one full circle in 2 seconds, its angular velocity is 2 pi radians divided by 2 seconds, that is pi radians per second. We can also connect angular and linear velocity through the relation v equals radius multiplied by omega. So, both types of velocity help us understand motion on a circular path, one in terms of angle, the other in terms of distance. Here's something fascinating. Even when an object moves at constant speed in a circle, it's still accelerating. Why? Because its direction of motion changes. This change in direction implies a change in velocity vector, which is the definition of acceleration. In circular motion, this acceleration is always directed toward the center of the circle, and we call it centripetal acceleration. The formula for it is acceleration equals velocity squared divided by radius. So, the tighter the circle or the faster the motion, the greater the required acceleration to keep the object turning. Let's now summarize the main features of uniform circular motion. First, the speed is constant, but the velocity changes because direction keeps changing. Second, there's always an acceleration acting towards the center. This is known as centripetal acceleration. Third, since there's acceleration, a net force must be acting continuously, even though the speed isn't changing. This might feel counterintuitive at first, but it's fundamental to circular motion. The force could be tension in a string, gravity in orbital motion, or friction in the case of turning vehicles. All of them serve to bend the path into a circle. Let's solve a practical problem to make things clearer. Suppose an object moves in a circle of radius 1.5 meters, completing one revolution in 3 seconds. We are asked to calculate its linear speed. We use the formula speed equals to times pi times radius divided by time. That's 2 times 3.14 times 1.5 divided by 3, which gives us 3.14 meters per second. This is the constant linear speed of the object along the circular path. It's moving steadily, but remember, its direction is changing at every instant. To wrap up, uniform circular motion might seem simple, but it's packed with rich concepts. The object moves at a steady speed, but the changing direction of its motion means it experiences continuous acceleration. This acceleration is always directed inward toward the center, and requires a continuous force to sustain it. Linear and angular velocities give us different lenses to describe the same motion, both tied together through the radius. Whether it's a planet in orbit, a race car on a circular track, or a flywheel in machinery, uniform circular motion forms the foundation of much of our physical world.